The schedule. After today, we've got 3 more weeks and then the exam. So that would be next week, we'll do the 2 labs on Wednesday. The week after, we'll do the exam. And then the week after that, we'll just be review and check out of lab on Wednesday. The final exam for this class is based on the published final exam schedule at Harper. So that is, check that right now so you can get it on your calendar. Yeah, it's based on what time this class is. So since we kind of fit in a couple different places here, since we're Tuesday, Thursday, so our exam will be in this block right here because we're Tuesday, Thursday, 2 to 3:15. Actually, I guess we can choose. We can either do the exam here or we can do it that might interfere with somebody's class. 2 to 4:40. Yeah, we have kind of a weird schedule because of our lab is at a different time. So I guess we have to do it here. So it'll be Tuesday, May 17th, 1:45 to 3:30. And that's actually a little bit shorter than our usual lab time. So the final exam, even though it covers the whole semester, is a little bit shorter than the other exams. I can make this bigger here. So it's Tuesday, May 17th, 1:45 to 3:30. This is the different classes that will be in that period. So since you're in this class, you should not have any conflict with other classes being at the same time. Any other exams being at the same time. And I don't have a room for that yet. It'll probably be upstairs in the lab room or one of the other rooms around there. I'll let you know when we get that. But that will be the final exam. Okay. All right, let's talk about namings. So we ended last time and we looked at some of these alkanes. We drew some isomers of pentane and of hexane. Today we're going to do 2 things. We're going to look at naming and we're going to look at drawing line structures, which is another even better, quicker way to draw these organic structures. All right, I'm going to start a new page, but we're going to go back to these and name them as part of this. So just like all the other naming we did many chapters ago, there are specific rules that you have to follow to come up with a proper name for an organic compound. We're going to go through those 3 steps now, and hopefully it will make some sense. It probably won't make a lot of sense until we start practicing it. So the rest of today, we'll pretty much be drawing different alkanes and practicing how to name them. All right, so this is our first one we're going to look at. This is one of the isomers of pentane. We know how to name the straight chain alkanes. They have those specific names that were in that table. So if you've got 5 carbons in a row with their hydrogens, that's called pentane. If you've got 6, it's called hexane, so on. What gets tricky, or at least different, I don't know about tricky, but different, is when you have this sort of a situation where it's not pentane. It's the same formula as pentane, but it's a different molecule. So what do we call this? And here's how we figure that out. And I'm going to try to color code this for the different steps. So the first step, the first thing you're going to do in any of these molecules is that you want to find the longest continuous carbon chain. And we kind of practiced this on Tuesday when we were figuring out whether things were the same or isomers. But what's the longest chain that you can make in a molecule where everything is connected? Everything is continuous. You don't have to pick up your pencil. And this structure, how many is it? 4. And there are various ways you could count that 4. Well, there's 2 ways. You could look at these as the 4, or you could look at this as the 4. And I'm going to actually circle that one. It doesn't matter which one you pick, but one of the common mistakes with these kinds of naming things is we always want to do the horizontal one as the answer. And sometimes that's not the answer. Sometimes it's the one that goes like this or something like that. So just for an example here, I'm going to pick this as the longest chain. You could also pick the regular horizontal one, same thing. But I'm going to pick this one just because it's a little less obvious. So that's the first step in naming, finding that chain. As you get better at this, more practice, you won't have to circle it. You'll just see it. And then the second part is going to be, the second step is going to be number the carbons and I'm going to use a word here that we haven't talked about yet. Number the carbons so that the substituents, so we're going to define that in a second, so that the substituents are attached to the lowest numbered carbons possible. All right, let's talk about what that means. So we're going to number the carbons, and they have to be numbered in order. So you start on one end, you go 1, 2, 3, 4. You start on the other end, you go 1, 2, 3, 4. In this case, there's 2 possibilities. Well, there's always 2 possibilities for how we could number it. We could start from one end, or we could start from the other end. So we can go 1, 2, 3, 4, or we can go 1, 2, 3, 4. We get 2 pieces of information from this. One is that we know how many carbons that chain is. Now, in a short one like this, you probably could have figured that out without writing the numbers down. But as these things get bigger and longer, it can help to number it so you don't skip any. So we know now what we call the parent chain, which is the main part of the chain, has 4 carbons. Does anybody remember what the name of a molecule with 4 carbons is? Butane, right? Did you remember that, or you just sat on that? Yeah. So that means that the last part of the name is going to be butane. And that reflects that long chain. So now let's talk about which numbering order we want to go with. The rule says we have to number the carbons so that the substituents are attached to the lowest number of carbons possible. What do you think the substituents are here? What do you think that word means, substituents? Well, that's what we want attached to the lowest number. Yeah, so substituents means, I define it as stuff hanging off that parent chain. That word substituent means substitute for hydrogen, so something other than hydrogen. But we can just think of it as we have this chain that we call this parent chain. Everything else coming off of it is called a substituent. So in this case, that CH3 is the substituent. I'll draw a green box around it. Call that the substituent. So which numbering scheme are we going to go with? Does the 1 start down there, or does the 1 start over on the right? Yeah, on the bottom. Why? Right. Does everybody see that? If we start down here, then this CH3 is on carbon number 2. If we start over here, then that CH3 is on carbon number 3. We want to go with the lower number. So that means that our first numbering was correct. And we should stick with that. Make the lowest number with the substituent. Okay. So then the last rule is to name the substituent. So our third rule will be to identify and name the substituents with the number they attach to. And we're going to talk about how we do that now. So to name a substituent, we need to recognize that the substituent is different from the chain itself, or from the overall or a neutral compound. A methane is CH4. That's the molecule of methane. This thing is kind of like methane because it only has 1 carbon, but it's CH3, so it's not exactly methane. So we have another word for it that we're going to use. So to name our substituents, we're going to drop the ane, and we're going to add a different suffix in the end, YL. So if we have a CH3 that's attached to a chain, we're going to call that methyl. So it's like methane, but methyl. And that's going to be true with other substituents as well. So a 2-carbon substituent is kind of like ethane, so we call that ethyl. What do you think a 3-carbon substituent is going to be called? So what would it be? Yeah, propyl. So those are our substituents. And we're not going to see any substituents bigger than that in these examples. All right, so now we have to name that. So instead of just butane, we're going to call this, with my colors here, we're going to call this methyl butane. And that's actually one word, methyl butane. And we need to specify where that methyl connects to. And where does it connect to? It connects to carbon number 2. So this is 2-methyl butane. Let's review those steps and how we use those to name this molecule. We found the longest chain. We numbered it so that the substituents were closest to 1. Then we named the substituent with the number. All right. So now we're going to look at some slight variations of this, how these rules apply to some different kinds of molecules, and then we're going to practice with a lot of different examples. All right. So let's take a look at this one. This is another one of the isomers of pentane. And let's see if we can follow those rules. So first, what is the longest continuous carbon chain?
Like 3 there and 3 there.
Yeah, so it's 3, right? And there's a lot of different ways we can make that 3. 3, 3, 3, 3. They're all the same. So you like the this one, right? We'll pick that one. All right, step 1, good. So what we can write down the end of the name then. What is that? Yep, propane. So that means the end of our name is going to be propane. Okay, now let's number that chain. Does it matter if we number from top to bottom or bottom to top? Why not?
Because the carbon was the second.
Yeah, because these substituents are both on the second carbon, so it doesn't really matter where we start. So we can go 1, 2, 3. All right. What do we have for substituents here? Yeah, we have 2 substituents, and they are both what kind of substituents?
Something the same like methyl.
Right, they're methyl. But now we have to account for the fact that there are 2 of them, and they're both on the second carbon. So one way to do it, we could say 2-methyl, 2-methyl. That's usually not how it's done. It's usually abbreviated and written like this. 2, 2. That tells us that there's one on 2 and another one on 2. If one of them were on 2 and one of them were on 3, it would be 2, 3. Although in this case that would be a different molecule, but we'll see those examples in a bit. So it would be 2, 2, and then instead of methyl, we say dimethyl to indicate that there are 2 of them. We can put that over here with these. Di is 2. We've used these before, right? So those same kinds of things apply here. So this molecule is called 2,2-dimethylpropane. All right, we good so far? So, all right, let's try some others. I'm going to put down 2 of them, and I want you to come up with some names, and then we'll look at them together and see what works. All right, so here are 2 examples. Use your rules and try to come up with a name for each of them. when you have two names, turn to someone near you and see how your name compares with theirs.
Those are also. No, it's not methyl. No?
I'm not going to say anything right now, so you have to think about that. So do they agree? Okay, I'm gonna write down the names I got, and then we'll talk about where they came from. For this one, I got two, three, dimethyl butane. What do you think? Yeah. Why 2, 3? Let's look at it. Our main chain is 4 carbons long. Right? That's the longest chain we can get. So when we number it, 1, 2, 3, 4, we see that the methyl substituents are on 2 and 3. So you've got 1 on 2 and 1 attached to 3. So that's the 2, 3. Okay. The next one over here, I got 3 ethyl pentane. Yeah. So here's our longest chain, or one of the possibilities. 5 carbons. 1, 2, 3, 4, 5. And then our substituent is a 2-carbon substituent. There's an ethyl instead of a methyl. That's one of these.
And the previous, we also had 2 substituents.
Yes. But in this case, they are separate. They're attached. One of them is CH3 and the other is CH3, and they're not attached to each other.
So the lowest is 2, it attached to the second one. This is why we ethyl.
Right. Because there's 2 of them attached together in the chain. All right. So before we go on and talk about the line structures, let's go back to these 5 isomers of hexane that we came up with yesterday and see if you can name all of them. Yeah. Oh, take a couple more minutes, and then we'll go on and talk about stuff. these names up here. That one's hexane. This one will be Dimethyl Pentane. And down here we've got Methyl Pentane. We did this one before, so this one's 2,3-Dimethyl Butane. And this one is 2,2-Dimethyl Butane. Any questions about those names, where they came from, or why I got one way that maybe you think should be another way? Is good. Okay. This also illustrates a good way to solve this problem that we were dealing with on Tuesday. If you're good with the names, then one thing you can do is name the different isomers that you come up with, and if two things have the same name, then they must be the same. So when we were drawing things that were kind of the same but just like twisted around a little bit differently, we could have uncovered that by naming them and then noticing that some of them have the same name. One common exam type question that you'll see with these structures is, it'll be something like, what's the relationship between these two structures? Are they isomers, or are they the same, or are they unrelated? And one way you can determine that is through the names. If they have the same names, they're the same. If they don't, then they're either isomers or they're unrelated. If they have the same formula, they're isomers. If they have different, then they're unrelated. All right. Sorry, you still writing? Yeah, go ahead. And then we'll talk. Good. Okay. Then we'll talk about line structures. All right. Drawing the structures as we've been drawing them is fine, but when structures get larger and when you want to draw them more quickly, that becomes a little bit of a problem. So we have another way of expressing structures that we call line structures, or sometimes skeletal structures. I don't remember which one the book talks about. All right, and it look like this. So we can start with our condensed structure for hexane like this. That's hexane, 6 carbons in a row, and that's called a condensed structure. A line structure for hexane looks like this. Kind of different, but a lot quicker to draw. And as we'll see, it gives us a little bit more information too. So one thing with the line structures that you may have noticed is if we're looking for 6 carbons, we can find them here by counting each end as a carbon and each place where lines meet as a carbon. All right, so that's our first rule. Again, we're going to detail some rules on how these things work. It's a way of abbreviating the carbon and hydrogen because organic structures are mostly built of carbon and hydrogen. Other things in these structures are not abbreviated, and we'll talk about that also. So first, we're going to assume there is a carbon at each end and vertex of lines. That's where the lines meet. So if we had that kind of a structure, we'd have a carbon here, here, and here. At the end, and then where the lines meet. That's the idea of a line structure. And this isn't really a step-by-step on how to draw it. This is just rules. We'll talk about how to draw it in a second. So because of that, we have to have kind of this zigzag structure. Because if we just drew it in a straight line, you wouldn't know how many carbons were in that line. That also ends up working out nicely because if we recall the model of the atom of methane, the model of the molecule, that was the angles that showed. So if we pull that back up here, let's draw hexane over here and look at what that would look like in 3 dimensions. So there's our line structure of hexane. But if we look at the 3-dimensional structure here of hexane, you can see that drawing that in a zigzag line actually kind of makes sense because that's what the shape would look like in 3 dimensions. We'd have carbon, 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 because of that tetrahedral structure that we looked at on Tuesday. So that part kind of makes sense. The second thing that you'll notice is abbreviated here is that there's no hydrogens. We don't see any hydrogens in that line structure for hexane. So how do we know how many hydrogens we have and where they are?
We have to count those vertices.
Well, yeah, we have to count the number of lines around it. So we know how many bonds carbon wants, right? Which is, how many bonds does carbon get? 4, yeah. So we've got 4 bonds to carbon. So that means that we have to assume that there are enough hydrogens on each carbon to fill carbon's valence, which is 4 bonds. So let's look at an example here. If we drew this line structure, let's look at this carbon right here. That's the carbon atom we're saying right here. Okay. How many bonds does it have to other carbon atoms? 2. You see those 2 lines coming off of it? So that means how many hydrogens does it have to have? Yeah. So that means it has to be 2 hydrogens here to account for those extra bonds. Let's look at another example, similar. Now we have a double bond here. So if we look again at that carbon right there, how many bonds are already attached to it? 3. So how many hydrogens need to be there? If it's got 3 bonds already, how many hydrogens do we need? Just 1 to get to 4. So that's why we don't need to draw the hydrogens in the line structures, because we know how many are supposed to be there. It just has to add up to 4 with all the bonds combined. And then the third rule of line structures, is that all other atoms are not abbreviated. And this including hydrogen on other atoms. So that means if we have a structure like this with an OH, we don't cut that H off of the O, because the reason for that is the other atoms don't have as clear rules about how many hydrogens or how many bonds this carbon does. So if we cut the hydrogens off the other atoms, we might be losing some information that we need. So that's why you'll see things like this, or like this. So other hydrogens on other atoms don't get abbreviated. And that's line structures. So let's practice now and think about how we draw them. Let's go back up again to our isomers of hexane. This is a good place to practice this because we've got a bunch of different examples here. And let's practice drawing the line structures. So to draw the line structures, you want to think of it a lot like the naming. You want to draw the longest chain first, and then add the other things as needed as they attach. So for hexane, we just did that one. 6 carbons in a row. So we're going to draw a zigzag of 6 carbons. Let's look down at this one below it, 3-methyl pentane. So the longest chain is how long?
Which one?
3-methyl pentane down here. 5. Yeah. So we're going to count 1, 2, 3, 4, 5. Doesn't matter if you start going up or start going down. Same thing. One common mistake, make sure that you always count 1 where you put your pencil down, not 1 when you make your first line. So it's just 1, 2, 3, 4, 5. And then we're going to have a methyl group coming off of carbon number 3. So carbon number 3 is 1, 2, 3. So there's a methyl group coming off right there. And we don't need to draw that CH3 on the bottom of that line because we know, because it's the end of a line, it must be a carbon. And because carbon has 4 bonds, it must have 3 hydrogens around it. All right. One more, and then you can do a couple. We'll look at this 2,2-dimethyl butane. Now, the way this is drawn, kind of down in this cross shape, is not going to be really conducive to line structures. So instead, we're going to use the name. So we know there's going to be 4 carbons in a row, butane. So we'll draw our 4. 1, 2, 3, 4. And then we need to fit 2 methyl groups on the second carbon. Now, there's a couple ways we could do this. We could go 1 up and 1 down. Or we could go kind of put them both on the high side like that. The common way to do it is like this. The reason for that is bond angles again. Remember, those bond angles are actually a tetrahedron. So even though those are closer to 90, the way we've drawn it here, these are really too small of bond angles. See how it kind of cuts in between there, and that becomes almost like a, I don't know, 50 or 60 degree bond angle. So that's a little bit too small. So we usually draw it like this instead. I would not mark it wrong if you drew it like this, but it's conventional to do that. Yeah.
But if we have more, how we will do it?
What do you mean? More than 4?
Yeah.
You can't, because carbon only has 4 bonds. So that's it. All right, so see if you can draw these other 2. Draw line structures for these other 2, 2-methyl pentane and 2,3-dimethyl butane. While you do that, I'm going to pull up the book so we can look at So we'll look at a couple of those problems after this. All right, got some structures. Should look something like this. So 2,3-dimethyl butane is going to be like that. And 2-methyl pentane, like that.
Can you explain?
Yeah. Oops. No. So first we're going to look at the parent name, which is butane. That's 4 carbons. So we draw 4 carbons. 1, 2, 3, 4. Okay. And since it's 2,3-dimethyl, that means we should have a carbon on number 2 and a carbon on number 3. So if we're going from left to right, 1, 2, 3, 4. That means we have 1 on number 2 and 1 on number 3. Yeah, you look like you don't believe me. That's okay? Okay. All right, so before we get into the book stuff, to practice this a little bit more, let's see if we can write line structures straight from the names. So I'm going to write some names here, and you'll see if you can draw the structures. I'm going to throw a couple other things at you here that see if you can figure it out. See if you can come up with structures for these 3 names.
What does it mean, chloro?
Yeah, see if you can figure that out.
establish the relationship between these compounds.
All right, so looks like some good structures over there. There's hexane, and you've got 3, 4. Right? Okay. So this one threw in something different. We still have hexane. Now it's 3, 2. But what do you think chloro means? Yeah, chlorine or chloride. So that means that instead of a methyl group on the 3, we're going to have a Cl there. And because that's not carbon, we don't abbreviate it or anything. We just have to list it as Cl. All right. And then the last one, ethane is just 2 carbons, which in a line structure is just a line because it's got 2 ends. So then we have to have our 4 fluorines on there at 1, 1, and 2, 2, which means 2 on carbon number 1, 2 on carbon number 2. Again, not carbon, so we have to make sure to have the F's on there. Okay. Questions about those?
That's one with names.
Yeah, good stuff. It's gonna take a little
Because
practice.
I wrote the first one 5.
Yeah.
That's 6.
Ah, okay. So one thing that helps with that, and that's a really common thing, there's nothing wrong with just writing the numbers. So after you write your line, go 1, 2, 3, 4, 5, 6. But you do have to know the words. Like, there's no easy fix for that. The list, it would be, let's see.
If you're right, 12. It's on page. Oh, wait, you said 11. Yeah, sorry. You said 3.
306.
Yeah. And you only need to know up to 6. All right. One last piece of this is that we can also have structures that are connected in a circle or in a ring. And we call these cycloalkanes. This kind of a structure has 5 carbons. So we call that cyclopentane. And to draw it in a line structure, it would look like that. So they're not tricky. There's nothing really tricky about them. They're a little hard to draw sometimes. But the main thing is just remembering to put that cyclo prefix on when you're naming a structure like this. So if we have something like this, We can name this. But in this case, instead of thinking about the longest chain, we see that there's a ring. And so the parent name becomes the ring rather than a chain. So instead of ending the name with something normal, one of the normal ones, we'd call this what? Go ahead. Yeah, this would be cyclohexane. And when we number this one, we have to number it in such a way so that the substituents have the lowest possible numbers, which means we're going to start at one of them and go around from there. We have to go around one way or the other. It doesn't matter which way, but we can't skip from carbon to carbon. It has to count 6 around. So in this case, the types of substituents that I see here, I see a methyl, and an ethyl. Ethyl E comes before M, so we do alphabetical order with this. So I'm going to start there and count around this way. Now, if you started up at the top with the methyl, that's okay. Well, I'm not going to be strict about alphabetical order here, but the correct way to do it is like that. So this becomes, whoops, sorry. This becomes 1 ethyl, 2, 3 dimethyl, if I can fit it in there, cyclohexane. We've got 1 carbon substituents on 2 and 3, those are called methyl. We have a 2 carbon substituent on 1, that's called ethyl.
But why we write like first 1 ethyl, it's okay. Then 1, 2, 3 dimethyl.
Mm-hmm.
Why we count 1? Because at the end,
Right, so this is 1 carbon here and 1 carbon here. This one is connected to number 2. This one is connected to number 3.
how what mine? You wrote mine.
And the ethyl, which has 2 carbons, is on number 1. This is an L.
No, I mean, yeah, before.
This word? This?
Yeah.
That's an L. Yeah. YL.
We start from the 1, we
Yep.
count 1. The end of the line 2, and the end of the other line is 3. Yes or no?
No, because we have to count around the cyclohexane, because that's our main part, our parent piece.
No, why a 2?
Oh, because we have 2 carbons here, 1, 2.
And we start from the middle or from the 1?
From here, because this carbon is part of the ring. So that one doesn't count. This is the next, this is the substituent carbon. Yeah, good question. What's the smallest cycloalkane? What do you think is the smallest that you can have in a ring like that? 3, right. Because if it's smaller than a triangle, it's not a ring anymore, it's just a line. So the smallest one is cyclopropane. What do you think the bond angles are inside cyclopropane? You ever remember your geometry? What's the angle inside a triangle? Yeah, 60. And what did we say the angle should be for carbons? Do you remember in that structure?
109.
Yeah, it's about 110, 109, 110. So the fact that these are 60-degree angles instead of 109 or 110 means that this structure is very strained. It's not great to be like that. It's very high energy. So cyclopropanes like this are very reactive, meaning they want to break apart and do other stuff because they're too constrained, they're too tight. If you take some models and you actually try to build that, you can like snap the models. You can't get them to close together because of that. And so that would seem to be the same issue with something like cyclohexane. What's that angle in a hexagon? Anybody know? kind of related to triangles. You think about triangles being in the inside here. Close. 120, because it's like two triangles next to each other. So it's 120. And that's bigger, so that would be like two stretched out. But actually, this is the most stable ring structure. And the six-membered ring, the hexagonal ring, is really important in all kinds of structures, from sugars to other important things in the body. So why is that? Oh, I shut it off. But let's look at our model again. And let's make a model of cyclohexane, and I'll show you what it looks like. So here's our cyclohexane, our hexagonal structure with two hydrogens on each carbon. But when we look at it from the side, what you find is that it's actually not flat. It has this kind of zigzag structure. So in that way, it can maintain the proper bond angles of about 110 in that tetrahedral structure, even though it's connected in a ring. So it kind of goes up and down as you go around like that. And if you go on and take, if you go on and take organic chemistry, you'll learn more about why this structure is important, and you have to draw it and all that stuff. Organic chemistry is no math, but a lot of drawing stuff. If we look at just the wire frame here, you can kind of see that structure a little bit better. So sometimes you'll see that in things like sugars, or in structures made from sugars, that kind of thing. You might recognize that shape. All right, so that's the cycloalkanes. Okay, we got about 5 more minutes. Let's do a couple more practice, finish up, and then we'll continue with this next week. So I want you to write names for these structures. You might need to come up with some stuff or look back a little bit to do this. All right, we're almost out of time, so let's take a look at this first one. We'll just go through how I would get this. I'd recognize first the cycloalkane. Those are usually easy to spot because they're in a ring. This one has 4 carbons, so that's going to make it a cyclobutane. Right, and then to number it, I'm going to start at one of the substituents and go around toward the other one. If you started down at the methyl, that's okay. Again, alphabetical order if you can, but it's not that important. So this one's going to be 1 bromo, 2, I'm going to run out of room, methyl cyclobutane. And then this one, this is one of those ones that could potentially trick you if you try to go around across the middle. You could count 1, 2, 3, 4, 5, 6, 7, but there's actually a longer chain here. Where is it?
8.
Right. So we're going to go 1, 2, 3, 4, 5, 6, 7, 8, or 1, 2, 8. So that's going to be our main chain. The substituents here are a little bit bigger because we've got a bigger chain here. We've got an ethyl, 2 carbon substituent, and this is a propyl, 3 carbon substituent.
I still mixing.
Yeah, you just got to learn that table. Yeah. And then so this one you would have to look up because it's more than 6 carbons, but the name then comes out to 4 ethyl, 5 propyl octane for 8.
Oh, we should write first the number which touch the.
Right. Yep. You got it. All right, that's it. That's all the time. So we'll see you on Tuesday. I guess, do you want to have a quiz on Tuesday on this stuff, or do you want to wait till the next week?
Only this stuff,
it's okay.
Just wait? Okay.
Yeah.
So then the quiz will be on the Tuesday right before the exam. Quiz Tuesday, exam Wednesday. So it'll be like a good practice review, I guess.
So when do you want to have this?
Not this Tuesday, the next.
Next Tuesday.
Yeah,
And,
the day before the
Wednesday,
exam. This Wednesday is lab. The next Wednesday, May something, is exam.
So next week, you have a quiz. After a quiz, you have an exam.
2 weeks. Yeah.
Exam is
Right? Is that you have to schedule it? Right. So. So this exam will be mostly on acids and bases, nuclear chemistry, and organic chemistry.
Nuclear and organic.
And acids and bases.
acids, bases, which one?
Acids and bases. Nicholas? So, acids and bases.
Nuclear, organic chemistry.
This is exam, yeah?
Mm-hmm. I mean, and other stuff, old stuff, but that will be the focus.
So on Tuesday we have 26, and next Tuesday on May it's gonna be 3. We have test. Yeah? May 3 test.
Can we review before that?
Yeah. So we'll finish this organic stuff next week, so that between next week and before the exam, we should have some time.